And we're live. Welcome, folks, to the MongoDB podcast. I'm having some technical difficulties this morning. There we go. I hope you're all well. Thanks for joining me today. We've got a wonderful episode of MongoDB Office Hours for you today. We're going to be joined shortly by Rick Houlihan. Today, we're going to cover a subject near and dear to my heart, data modeling and migrating from relational technologies to document databases like MongoDB. So as you come into the stream, let us know where you're from. It's great to see everybody saying hello. We've got a lot of folks joining the stream. Hello, Raphael. Hello, Masha. Arpan. Let us know where you're joining the stream from. I'm on the East Coast of the United States in a little town called Yardley, just outside Philadelphia. And as you know, I am a developer advocate at MongoDB. I've been working with MongoDB for well over 8-9 years now. And I'm so excited to share some of the things that I've learned about data modeling. There's Rick. Let's bring Rick onto the show. He can share his experience as well. Rick, it's great to see you. When you're building an application for relational technologies, you follow a set of rules, CODS rules, that state that you should separate data so you avoid duplicating it. And Rick and I are going to get into why that might not make sense in the context of a document database. So let's just continue on. And I want to cover some of the history. So many of you may not be familiar, but CODS rules were developed back in the 1970s. And that's when, way back when, people dressed like this. And this is COD himself. This is the guy that came up with these rules that how you lay data out for a relational database. He worked for a company called IBM, and they used computers that looked like this. It's a dinosaur. And they had disk drives that looked something like this. They were giant, massive, and super, super expensive. By the way, that guy looks like an Oompa Loompa. But they were super expensive. Disks cost so much money, heaps of money, just about this much money. And it was really important that you didn't duplicate the data on disk. Back then, a megabyte of storage cost you about $9,200 for 1 megabyte. You've got so much more than that available on your phone alone. Now it's about 0.00004 or 2 cents per megabyte. So it's approaching zero. So why are we still leveraging this same methodology where we're trying to save on disk space at the cost of your time, the developer, which is much more? So you end up with this situation where you've got your data strewn all over the place and separated into these massive number of tables, and getting that data out, you need to do these massive joins using select. This is CODS rules of normalization, and this is what is used in a relational database schema. So that was way back in 1970. Today, things are much different, and you can watch that line drop down to zero. It's representing the cost of disk space. So it's approaching zero. Back in 2007, when MongoDB began, it was so much less. But it's not only the cost of disk space that is impacting the way we should change the way we think about storing data. It's also like the logical view of how you store things in the world. Data is all around us. And if I were storing my car, I wouldn't store it in buckets, break it down into the component pieces and store it in different buckets. I'd store it in a garage like this. And that's kind of how MongoDB looks at data storage. So the concept that data that is accessed together should be stored together is super relevant. So I'm gonna open the conversation up with Rick. I hope that set the stage. We're talking about a shift in approach about how we think about storing data. Does that make sense to you, Rick? I think
yeah, no, absolutely. So, I mean, a couple of points there that you kind of brought up that I think are relevant. Obviously, cost of storage is definitely a factor. And, back in the day, storage was expensive. But the reality of it really came down to that the cost of the relational database wasn't really about, saving, money on storage, right? That was kind of a byproduct of the normalized relational model. I mean, if you look at Edgar Codd's seminal paper, right? Relational model of data for large shared data banks, right? The first line in the opening abstract is to say that future users of large shared data banks must be insulated from understanding how the data is stored, right? And I think the key takeaway there is really about, was people need to ask questions, right? Data is not always a static thing. Get me this object and I'm done, right? It's, there's all kinds of random questions people need to ask. And up until the relational database and the introduction of the relational database, that was a really difficult thing to do, right? I mean, actually, the hierarchical management systems of the day, they had, they were great for OLTP workloads that needed that piece of data, and they would update that piece of data, and that's all they needed to do. But when someone needed to ask a question, now I had to go to a coder, and I had to get someone to write a program to go and digest all that data and understand and restructure it and produce the output, right? That was a lot of work, and it was very expensive. And so the idea that I could have this kind of abstract data model that I could ask questions against, right? That was a powerful thing for the relational database. And in order to make that happen, and this is one of the things that I think people kind of lose sight of, the normalized relational model was built and was tightly coupled to the storage engine of the relational database, because the storage throughput and the CPU bandwidth in 1979 did not allow people to run ad hoc queries on hierarchically stored data, right? The hierarchical management system was, you get what you store. You don't get anything else. And then trying to run an ad hoc query on data that's denormalized was like, oh my gosh, it outran the systems of the day. But that's not the case today, right? We look at this, at the power we have, the CPU throughput, the bandwidth, and the throughput on storage we have. It's tremendous. And we can actually write those ad hoc queries. And this is the key when you start to understand. It's not just about data that's stored together, should be accessed together, but it's about driving efficiency, right? Yeah. If you think about the relational model, it spends a lot of time joining tables. You put that diagram up there, show those thousands of tables, right? If I want to query that data, I'm joining tables, right? Joining tables is expensive. In a NoSQL database, we want to avoid joining tables. And there's two ways to do that. The first way is to embed the data into a complex document. And the second way is to store all your documents in the same collection where they can be indexed on the same index, right? And this is what we're here to talk a little bit about today is, why is that better than doing this normalized, joining of tables? And what it comes down to is CPU efficiency. If I can save time complexity, if I can reduce the time complexity of the query that is accessing the data, then I can use less infrastructure to support that workload than the relational database requires. And that's the key. That was the key criticism of the relational database in 1979, right? It was the cost of the join. Everyone back then, even Edgar Cott himself talked about this in his paper. He talks about how denormalization, introducing strong redundancies, he calls it, introducing the strong redundancies into the stored set, will actually reduce the load on the CPU for those queries that are relevant, right? And that's a key concept, because in NoSQL, what we think about is, look, I want to optimize the high velocity queries, right? The ones that are running hundreds of times a second, thousands of times a second, those are the ones I care about. I mean, the one that runs once a day or once an hour or whatever, that complex question that people are asking, or the ad hoc query that the analyst needs to run, I just need to be able to support it. I don't necessarily need to be as efficient running that as I possibly can be. And that's really the key to the relational database. The relational database is agnostic to every access pattern that you want to throw at it. And it has kind of a lowest common denominator data model. And it's just not going to be really great. It's not going to be optimized for anything, but it's going to be able to answer any question. Right. And the NoSQL database, what we're going to do is we're going to optimize for very specific access patterns to drive efficiency in the platform. And maybe we're going to sacrifice the efficiency of those complex queries, but they don't run very frequently. So I don't really care about that cost. So that's why I would kind of caveat your discussion there. You talked about savings on storage. Absolutely. We can do that. or cost of storage versus, compute, whatnot. But it's really about driving efficiency in the CPU.
Yeah. I love that. That's what it always comes down to. I think we're application developers, and we're responsible for designing the data storage that our applications use, but we're also performance engineers. I think every one of us at the end of the day. That's right. I did want to talk about documents. So we're gonna talk about transitioning from relational technologies. There's great questions coming in the comments. Please feel free to ask those. I'm going to be going back, and we'll try to answer some of those questions. But let's take a look at the document model, a closer look at documents. I think you can see that okay. So when I talk about documents, I was at the AWS Summit yesterday, or was it yesterday? Yeah, it was yesterday. Oh my goodness. or the day before. I don't know. My head is spinning. But I had some great conversations with some folks that came to the booth and asked about MongoDB. And when I mentioned document database, I got some quizzical looks. And the first thing out of a couple people was, do you mean PDFs or Word documents? No. And while you can store those things in MongoDB, you probably don't want to. They're probably more applicable to like an S3 bucket or something like that for those binary objects. What I'm talking about when I say document is a JSON-like structure, key value pairs. And if you see what's on the screen there, it's separated by braces, and there are key value pairs in the middle. That makes up your object. Objects exist in a definition of a key with a value. Keys are always going to be strings, and the values, they can be strings. They can be really rich objects, actually. So you can have embedding, where you have an object in another object. But when we talk about how we store data for MongoDB, it's not just straight JSON. We're not storing JSON on disk. I think everybody knows what JSON is, JavaScript object notation. JavaScript object notation doesn't have a concept of anything beyond numeric data and string data. Like, it'll understand an integer, but it's not going to understand what a date is versus a string that's July 1st, right? So when we store data on disk with MongoDB, we store some extra bytes with that date, with that data. And that's going to give the application that's referencing that object off of disk an understanding of what data type that is. So there's about, I don't know how many data types there are, Rick, that we support. Floating point, date, you're on mute. Floating point, date, GeoJSON is understood as a distinct data type.
I mean, that's one of the values, obviously, of a document store like MongoDB, is to be able to type your attributes, right? There's, and that is, there's I don't know how many types we have, but there's many, right? And so being able to store data as its native type, interpret that data, that's definitely part of the power of what we call BSON, which is our document structure, which is kind of a extension or a superset of JSON, right? Is really what it comes down to.
Yeah. So that's what a document is for us. I think I might have one or two more slides. We're going to talk about things today. If you're interested in looking at what MongoDB looks like, you can start for free at mongodbcloud.mongodb.com. You can get started for free. No credit card required to get started. This is our Atlas database as a service. We also have a nifty user interface tool called MongoDB Compass that will allow you to connect to your databases in MongoDB Atlas or wherever they are. And you can edit and manage your data using MongoDB Compass. You can also visualize. It's got some great schema visualization capabilities. So let's think about our application. When you're developing, I want to touch on this with you, Rick. The process for developing an application, when you're building it with a relational technology behind you, these are the basic steps as I understand them. Like, you think about what your app does, you take a look at what your data looks like and maybe the tools that you use. But with MongoDB, I'm missing a slide, but you really are focusing more on the data, right? Like, how does the process differ when you're developing for relational and then when you migrate to a MongoDB document database?
Yeah, sure. So, I mean, that is a key aspect of the technologies is, with a relational database, essentially we define this logical entity relationship diagram, and we're going to create a table for each entity. And if there's a many-to-many relationship, we might add a mapping table between those two entities, but it's pretty much cut and dried. Once we have that entity relationship diagram, we know what tables to build more or less in the relational database, and we can go ahead and do that. We're going to start writing queries and all that kind of stuff. But what's interesting about the NoSQL database is that we actually have to understand, in order to be able to do things correctly, be able to maximize the efficiency of the model, we need to understand what the access patterns are against the data, right? Is it a write-heavy workload? Is it a read-heavy workload, right? I mean, there's different techniques to how I model the relationships in a NoSQL database. I can choose to embed complex subdocuments and create a rich embedded document structure. That's a great pattern for a very read heavy workload, because if I need to get all the data all the time, and I'm never updating the data very much, then let me go ahead and get a big large blob with lots of embedded documents in a rich relational structure all in one big giant document. That's great. However, most applications don't work that way, right? Most applications actually use data in bits and pieces. One of the things we found at Amazon when I was running the black belt team for Amazon retail, and we were moving 10,000 workloads from relational database to NoSQL, what we found very quickly was that 70% of the access patterns in those OLTP workloads accessed a single row of data on a single table. Okay, a very small amount of data, and 20% more they accessed a range of rows on a single table. And at first you think, well, that can't be right, but then when you think about it, OLTP workloads tend to be very write heavy. Okay, I can in the thousands of workloads that I have reviewed, very few read heavy OLTP workloads. Right, they're about 10 to 20% of the workloads I work with are read heavy. About 70 to 80% of the ones I work with are extremely write heavy, and those write heavy workloads, they're hitting little bits and pieces of data. And that's really important because when I structure the data on disk, if I'm creating large relational structures and embedded documents and then I'm updating little bits and pieces of the data in those documents, right? Or I'm accessing just a little sub document, essentially I have to access the whole document just to get a piece. Or I have to write the entire document just to update a little chunk of it, right? So that can be a very inefficient way to use the database. And so there's other ways that we would structure that data in small documents. We would push that data into a shared collection, and then we would index a common attribute. As a matter of fact, I could share my screen here and show you a little bit of what that technique looks like if we want.
Yeah, sure thing.
Let me go ahead and do that. Share a screen. And where is it? There it is. Share. All right. Is that coming
great
up?
Question. I want to address that. Yeah. So we'll do this, and then I want to address one of the questions about JSON stored in relational columns at some point. We'll address that.
Oh yeah, absolutely. I can certainly have. As a matter of fact, I can answer that question really quick. Please don't do that.
Yeah. So here's the question. In fact, some RDBMS like. Go ahead.
Yeah, some RDBMS like Postgres support JSON, JSONB, BSON, type columns. So one of the things about row column store, and this is where they bolted JSON onto the storage engine of most relational databases, right? It's not just some. I think almost all today support some sort of document type attribute. And the reality is that row column stores don't do very good with JSON data, and the reason why is because they don't like their row sizes to vary. Okay, a relational database expects every row to be the same size. And as a matter of fact, Oracle, Postgres, MySQL, that row size is 2 kilobytes maximum. If you hit 2 kilobytes, then you're going to extend that data into what they call off-row storage, right? And that's so 90% of the workloads that I see in relational database using document storage or JSONB attribute, whatnot, this is the problem they run into. And if you want to, don't take my word for it, just do a quick Google search on JSONB performance cliff. Just go ahead and Google that and then watch the video that comes back. It tells you exactly what happens underneath the covers in the storage engine. Even the JSONB team, the authors of the JSONB, plugin for Postgres acknowledge that there's a performance cliff at 2 kilobytes. You're going to fall off the edge and it goes into the tank. This is where document stores like MongoDB, true object databases, they excel because we use append-only file systems. We don't care about the size of the document in a collection. They can vary from kilobytes to megabytes, and it's not going to impact the performance of the data retrieval. Whereas in a row column store like Postgres or Oracle, MySQL, you name it, any relational database, as soon as you hit that 2 kilobyte limit, man, your performance is going to go off a cliff. So, works pretty good when you're using little tiny chunks of data, but modern apps these days, anyways, hope that answers the question. Like I said, you don't have to take my word for it. You can search Postgres, JSONB, performance cliff. You will get a very good description of what the problem there is. All right, so let's talk about relational data. How do we do this? Again, large embedded documents are great for read-heavy workloads. So if you think like a product catalog, right, where maybe, I need to get products by type or sort products by price or something like that, then, large embedded documents that for each project or for each product, that's a pretty good use case because product data doesn't update very frequently, right? But let's talk about an order processing use case, for example.
Okay, can I pause you real quick though? I want you to do a Command plus, make that a little bigger so.
Oh yeah, absolutely.
There we go.
That better?
Much better.
All right, there we go.
Yep.
So let's just say this is a model of a collection. We're going to have many different documents in this collection, right? So I got an order document, right? I might have order items in the document. So we'll call them order item 1, or we'll just call it I1, and that'll be an item. And then we're going to have shipments, right? So we might have a shipment. And the reason I'm going to separate these things all into different documents is because, again, if you think about the processing of the order, I'm going to let's take like the Amazon shopping cart, for example, right? This is kind of what this use case is built on. Items kind of have a life cycle independently of each other, right? They're going to get updated independently. They're going to get added to shipments. They're going to get, the status is going to be different. And at different times, they're going to be updated in different ways. And so if I put all this data into a single order document and I embed all these complex subdocuments, and every time I update an item or I add a shipment or I update an invoice or whatnot, then I have to read the entire order history, right? And that could be a lot of metadata, right? So we don't necessarily want to do that. So let's say inside my order document, I'm going to have an embedded subdocument that describes, the metadata of the order. This would be like the shopping cart metadata, right? And then I'm going to have an attribute here I'm going to call related to, right? What else am I related to inside this collection? So this is when you're doing write-heavy workloads or workloads that access subsets of the data independently of each other, you're going to want to create structures like this that kind of reference other documents within the collection. And in this case, the order document is actually only related to itself. And I'll show you why we care about that in a second. But let's go ahead and add that similar data to the item and the shipment. And so in this case, we've got some data. Now the data for the item is going to be different than the data for the order. Think of this as like the rows on the table, right? So if I had an items table and an orders table, the metadata, the rows would exist inside of this embedded subdocument, right? But this item, what is the item related to? Well, the item is also related to the order that it belongs to, right? So in this case, we'll just tag it with the order ID as well, right? So now we're going to go ahead and save that. Let's just copy and paste this because everything is going to have a similar data structure, but what's going to live inside of this data blob is going to be different depending on the item type or the document type on the table. So now we got a shipment, right? So shipment gets created. What's in this shipment? Well, maybe a couple things, right? So the shipment's related to the order, but it's also potentially related to the items that are in the shipment, right? And so let's say, okay, this shipment contains item 1, right? And that brings back another dimension here. What did I do? No, can't have a period there, comma. Save that. Apologies for the noise in the background.
Oh my goodness, what's going on?
Yeah.
you gotta get crisp. Crisp is a good extension.
To knock out the background noise.
Knock the background out, yeah.
In 1 second, I will go over there and hold off for a second. As a matter of fact,
are you building a house?
Yeah, I've got some construction underway here.
Okay. Building documents and building houses.
Absolutely. So, the other thing that the item is related to is it's, related to the shipment that it's in, right? And let's say, so what I'm trying to do is I'm trying to set up different access patterns here, right? So now what I'm going to do, I've got these 3 things. I got orders, I got items, I got shipments, right? And what I really want to do is I want to be able to get everything that's related to an order, everything that's related to the shipment, right? So what I'm going to do is I'm going to index the related to attribute that we're seeing here. And if I create that index, now if I query where order ID equals 01, what do I get? I get everything. I get the order document. I get the items that are in the order. I get the shipments that are in the order. And the interesting thing about this
on the index.
Right, it's just on the index, right? Yeah. So, and this is just an index lookup, right? So this is not a join, right? If you think about it, and if I put these 3 things in 3 different tables, hang on 1 second. I'm sorry, I really apologize for this, but I got
no worries. I'm gonna bring the audience up to speed with what we're doing. So you go take care of that. I'll do some. I'm trying to here. There we go. Hey, so thanks for joining us, everybody. We are in the process now of building some documents with MongoDB. And Rick has a handy tool that he built. It's called the MongoDB Index Modeler. And what he's doing is modeling some documents. He's in the process now of creating an example set of documents for an order and item database. And he's showing us how you can effectively create indexes for data that is stored in multiple collections, I think, right?
All right, I'm back.
That's okay.
Yeah, this is one collection.
Okay.
Yes, this is we have a collection called data. Inside the collection called data, I have 3 documents. We've got the the order document. I've got a document for each item that's in the order. I've got a document for shipments that are associated to the order. And if you think about, again, the data lifecycle here, when I place an order, I might know all the items that are in the order, but if I create a shipment, I don't know what the shipment information is until later, right? So if I add the shipment as an embedded document inside the order, then I'm going to actually have to write the whole order document again. So the idea here is that by creating these small documents that are indexed together, I'm creating a better structure for a write-heavy workload, right? If this was a read-heavy workload, like a product catalog or something like this, where those documents aren't being updated independently of each other at high frequency, then it makes more sense to use a rich embedded document structure, right? So this is, I think there was a question earlier on, is when to use embedded documents, for a write-heavy versus read-heavy workload. So they were kind of answering this question here, is that if you think about the life cycle, and let's talk about that for a second. If you think about the life cycle like a shopping cart in Amazon, right? And we all know the Amazon shopping cart, right? When I create a shopping cart, I start adding items to it, right? Do I add all the items at the same time? No, of course not. I add items one at a time, right? I go through the catalog and I say add to shopping cart, add to shopping cart. Now, oftentimes when I add these items to the shopping cart, and I know this because I actually worked with the Amazon shopping cart service team, oftentimes when you add items to the cart, you don't buy them, right? They just sit in the cart until you actually go to buy something. And then someone looks at the shopping cart and they say, oh, I don't want this. I don't want that. I don't want this. I don't want that, right? Now, guess what happens when I delete an item? I delete them one at a time. So if you think what's happening, and this is exactly what the shopping cart service team found at Amazon, was when they first told me we could never use NoSQL because it's too expensive. And it's because that's exactly right. Every time they added an item, it was also incurring the cost of every other item that was in the shopping cart, because that's what they did. They created a large document, essentially an item in DynamoDB, and they embedded each item in the cart into that as they were added and removed. And that increased the size of the document to the point where it was costing them more and more and more as people added items and then, removed those items, right? So the solution was doing exactly this, essentially creating a bunch of items on the table that were small, but partitioned together, right, by order ID. And that's what we're doing on this index. I'm partitioning everything by order ID, right? Now, let's say, for example, I want to get all the items that are in a shipment. Right. This is what we've done here by creating this relationship to the shipment in the items. Right. So when I add a shipment, I'm going to go ahead and decorate the items with the shipment that they belong to. Now, again, if I have, as you know, when you check out from Amazon, sometimes it says will arrive on Tuesday, will arrive on Thursday. Right. And you have an option to say give it all on my Amazon day or whatever. But as you can imagine, that's multiple shipments, and those shipments then get created independently of each other, and items are associated independently of each other. So this is all just an example of an application that's using data in bits and pieces, right? As most OLTP applications do. If you think about how it would interact with the relational database, right? How would it do that? It would interact with the rows of the tables. And so that's what we kind of want to do. In the case of a write-heavy workload, we want to work with rows on tables. We don't want to work with large, big embedded documents, right? Now, again, flip the script, and if it's a read-heavy workload and updates are infrequent, the problem with doing what I'm doing right here, okay, is that when I read the data, okay, so which is actually the less frequent access pattern. If you think about it, how often does a user check the contents of or the history of an order compared to the individual pieces of the order being updated in the order lifecycle, right? The individual bits and pieces of that order will be updated many, many times. But the user is only going to check the content or the status of the order once or twice, right? As he's waiting for things to arrive. So the read is infrequent. But when I do read, what ends up happening here is, since these documents, all these little documents get created over time, right? And not at the same time, they get kind of written across the file system. And when they get read back in, they get read back in with bits and pieces of data that aren't even related to them, right? Other documents that were written at the same time, they kind of fit in the same storage block, right? So this can cause cache churn. And this is why small documents with these related to attributes, they're not really good for read-heavy workloads, because you're just going to start churning your cache. And if you have a really large data set that doesn't fit in memory, this can cause a lot of file system thrashing. So this is really good for write-heavy workloads, not so good for read-heavy workloads, right? If it was a read-heavy workload, I would create a large embedded document for the order. I would create, embedded sub-documents for all the items and the shipments and the payments and the invoices. And if my primary access pattern was get order history, and I did that 10x for reduce the read pressure on the file system. Right. So these are the kinds of questions that we always go through when I talk to customers, and we're working and going through their workloads and understanding how is the application using the data. What are the write patterns? What are the read patterns? Right. Which is the heaviest access pattern? Let's optimize for that. Right. So in this case, what I'm trying to do is optimize for those high velocity writes that are occurring across all these little tiny bits and pieces of the items that are related to the order. Right. Whether it be shipments, items, the order metadata, right? Invoices, payments, whatever else I want to add into this, right? I can add easily, let's add, a payment, pay one, P1. Oops. And now we got a payment object, right? User, was sent an invoice. They bring the payment back. And again, it's the same data for the payment will be slightly different, but the related to is 01. Now I added that into the relationship. And if I look at the index and I select by 01, guess what comes back? That new payment that I just added. So you can see how from an OLTP workload perspective, I need to process a payment. All I had to do was insert that little small document into the collection and I'm done. Now, some day later, most of those orders, no one's ever going to look up those payments in the context of the order. You see what I'm saying? So only when a user comes in and looks at the order history does he actually need to see that. And that's going to be very infrequent compared to the number of payments that are actually written into the system. So I'm driving a lot of efficiency by allowing the workload to create small documents that are related to each other, as opposed to embedding all those related documents into a single rich document. Right. This is but again, one versus the other. It all depends on what the nature of the workload is. Is it write heavy? Is it read heavy?
Yeah. Right. So I want to pause for a moment, take some of these questions. What we're building is, yes, Noah, it's in the same collection. And I want to touch on this question from Chris E. Is the cost for CPU and memory usage less if we keep the same collection?
That's the bottom line, right? I mean, if we're not using dollar lookup, then we're not joining. If you think of the relational, dollar lookup is a join. That's what it does, right? It looks at it, and hopefully it joins, it merge sorts documents from two collections that are retrieved on indexed attributes, right? That's the most efficient dollar lookup, the most efficient join, and that would just be a pure merge sort of the results, right? And that's exactly what a relational database does, right? It merge sorts data from tables that are indexed on attributes that are related to each other, right? And so what we're doing here is essentially I'm taking all the rows from all those tables and we're shoving them into one collection, and I'm drawing the index on a common attribute, and that's creating a pre-joined collection of data. Yeah. Essentially, that's what these index partitions are. This is a joined view of many documents of different types, but they all live in one collection. So, and the reason why this is effective, and so it is because the time complexity, right? I mean, think of the time complexity of a merge sort versus the time complexity of an index lookup, right? I mean, it's O log n to get an index lookup. It's O log n plus n log n plus n log, I mean, it just doesn't, it goes on and on for joining tables. And actually time complexity gets worse and worse as you add more tables. So if I put all this data on orders, items, shipments, and payments, and I said, okay, select all from star from, orders, interjoin, items, interjoin shipments, interjoin, you know what I mean? Or group by order ID. I mean, that's a lot of work that the system is doing underneath versus go to an index lookup on order ID 1, right? That's going to be so much faster. Right.
Here's another good question from Sarab Sen. He says, MongoDB also uses B trees and RDBMS uses B trees. Then how MongoDB stores JSON in an effective way?
Effective way. Yeah, that's a really good question. We talked a little bit about row column store and how, the row column storage engines need each row to be the same size in order to be efficient, right? They expect every row to have the same number of columns. They expect every row to have a maximum size of X. If it exceeds 2 kilobytes, they're going to use off-row storage for everything else. That's where they become inefficient because they're storing data in 2 places, right? If you look at how Wired Tiger works and how an object store or document store like MongoDB works, it's different. Essentially, each document is written to disk in its entirety. And the B tree it's a pointer to the file on disk. Whereas in relational database, the B tree has a pointer to the row in the row column store, right? So it's a row location in a relational database versus a file location in an object store. Okay, so essentially you're going to be faster in many ways working with little tiny bits of data in a relational database, but as soon as you see join, you're going to get torn apart, right? And that's where, what we found at Amazon was that even though 90% of access patterns hit a single table, 70% a single row, it was the last 10%, right, that were driving 50% of the infrastructure utilization for those joins, right? Yeah. So whenever you see like a user landing into a customer portal and getting a complete view of my customer account, right? Something like that. Anytime I'm sending a query down to the database and doing join to produce a view that the customer can use, we can recreate that exact same experience in a single collection, single table, embedded document type of data model, right? Using one or the other of those patterns, depending on read velocity versus write velocity. I can recreate that same experience for the customer using much less resources. And that's the key. If you think about the relational database, it relies on CPU efficiency to drive low cost, right? If you think about the NoSQL database, it uses data model efficiency to reduce the amount of CPU required to support the workload. That's the two differences there. So this, and also, side point, that is actually the reason why NoSQL databases are now separating themselves from the relational databases, because CPU efficiency is no longer tracking to Moore's law predictions, right? It has not been for a decade. And so you're starting to see that separation of cost efficiency, right? This is what Amazon noticed, right? When we started the project we called Rolling Stone, which was that mass migration away from relational technology, it wasn't go to NoSQL, right? The original mission was get rid of Oracle, because Oracle was expensive and it was embarrassing to talk about how we had all these great database services and then Larry get up on stage and say, well, why are you my biggest customer, right? So that whole mission, that didn't start off as move to NoSQL, right? What happened was the teams that were choosing NoSQL were coming out the other side with more cost-efficient solutions. They were saving money. And the teams that were doing lift and shift into RDS, well, guess what? They were paying pretty much the same cost in infrastructure. So, Werner's team looked at that and said, there's something going on here. And they pulled back the covers. And that's when they figured out that, oh, wow, cost efficiency is CPU. That's where it's all about. If you want to save money today, you need to drive CPU efficiency. And that's where NoSQL databases start to excel, right?
Great. So there is a question about real live queries and index creating in this episode. Are we going to cover any of that today, Rick?
I was planning on, again, this is a theoretical data modeling discussion. So I didn't really have any data loaded at this point. So we could get into that if we've got some time, but it's, again, the concepts here are really what we're trying to get across.
So we'll look to cover that in a future episode, Chris. We'll show some real live examples of data. So this show is scheduled to happen on the last Friday of every month. We're doing MongoDB Office Hours with myself and Rick Houlihan. So make sure you subscribe on YouTube and follow on LinkedIn so that you get notified. We're broadcasting live today on LinkedIn and YouTube. And of course, you've always got access to the MongoDB podcast on every podcast network. So make sure you subscribe across all of those channels to be notified when we have new episodes coming out. Where do we go from here, Rick?
Well, I mean, just interesting enough, I noticed a little conversation going on here about one of my former technologies that I used to represent. It was DynamoDB, and folks are saying DynamoDB is a key value store, not a document. And somebody replied with exactly the right question with the response, which is, no, it's not just a key value store. And that was one of my biggest frustrations at AWS, is it actually does support range queries on secondary attributes. But where it falls down is the robustness of the API, feature functionality, indexing options, right? It's kind of like if you have a really basic use case, okay, maybe it works well for you, but you're always going to run into that situation of, I just need X, right? And this is one of the reasons I've called this out, is because the developer data platform that we provide with Atlas is really, it's built with a purpose. And the purpose is to provide the functionality that developers need, right? And
Mhm.
not purpose-built solutions that provide silos of functionality that developers have to cobble together, right? So
Yeah.
this is where MongoDB starts to accelerate beyond, some of our partner offerings, is that we provide a more complete, more robust solution, right? So I just had to call that out because for two reasons. One is I don't like it when people call DynamoDB a key value store, because it's a lot more than that, but it's also not everything it needs to be, right? And that's why I'm here, right? So
yeah. So
anyways,
Yoav wants us to touch on collections. I'm not sure exactly
okay.
what he's asking, but maybe
Yeah, no
explain
problem.
the
This is
hierarchical model.
right. So, so the way I look at a collection, it's funny because we got a lot of documentation that kind of calls this, it says the collection is like a table in a relational database, but that implies that a collection is a homogeneous, kind of row column store, right? And it's
Mhm.
not. It's an object store. So if you think about a collection, in my mind, and kind of what I'm showing you here, is the collections are actually like the catalog in a relational database. Okay. There are no
Mhm.
tables, so to speak, in a
Yeah.
NoSQL database. There's only one table. There's one collection. It's where everything goes, right? And so if you think about a collection supports a workload to me, right? Just like a catalog supports a workload in a relational database. A catalog may contain many tables. A collection might contain many document types, right?
Yeah.
A document, and that's all, right? So a table in NoSQL or in a document store like MongoDB is actually a collection of documents that live within a collection itself, right? A group of documents that live in a collection. That would be the contents of a table. There's no table structure anymore. The idea here is we want a container of data, and I want to query the container. I don't want to have to join containers. As soon as you start creating tables, you start creating structures that need to be joined. As soon as you do that, you're increasing the time complexity, right?
Yeah. And I'm
So,
following
like, when
what
is it good
Yoav.
to separate them? Oh, this is a good question too.
It's a great question. This is the logical leap. It's the logical leap. The next logical leap when you start to think about collections versus tables. Well, when do you separate them?
Right, because there are times it makes sense, and so where
Yeah.
where I like to draw those boundaries is where, okay, look, we have like data lifecycle requirements, right? So you think about like time series data. In time series workloads, typically you've got like raw ingestion of time series data. You're going to be running some summary aggregations. You're going to store those summary aggregations someplace. I don't want to store those in the same collection because the raw data is going to age out, right? And I'm going to want to drop that. And the most efficient way to age out data in any database is drop the table, right? Drop the collection. I don't want to create TTLs on my time series data because I got to pay for those deletes. And so what I really want to do is I want to time box the raw data. So I'll create a time box collection by day, for example. I'll gather all my raw data. My time series data flows into this collection every day. At the end of the day, I'm going to run my analytics against that. I'm going to aggregate, summarize, do whatever I need. I'm going to write out my, maybe 15-minute summaries, right? 60-minute summaries, whatever it is I'm looking to create. Those go into my summary collection. And then at the end of the day, I'll just drop the raw data collection, right? Just completely just blow it away. A drop is free, right? TTLs are not. So that's a good example of why do I want to separate the data. And so that's where you start to look at where does it make sense to separate the data into different collections? It's where you have different data lifecycle requirements on that data and you need to manage it in bulk. That's one example. I'm sure there's others, but that's it's always, again, it depends on the workload, right? It's really what it comes down to.
Absolutely. Okay, so there is another question that's not really related, but I do want to answer it.
Sure.
So Vignesh is asking about sharding, which is MongoDB's concept of partitioning the data. You want to take this one, Rick?
Sure, absolutely. So all NoSQL databases work the same way, right? We create a key space, and that key space is then chalked up across multiple shards or partitions to be able to increase throughput, right? So what we're going to do with the shard key is we're going to try and group data on a dimension that makes sense and that evenly distributes that data. So if you can imagine, like here, I've got, a natural shard key, and my data right here would be order ID. Right. So as I scaled this order processing workload, I would create a shard key on order ID, which would ensure that as the data routes around, right, everything that is related to the same order that has a related to of 01 will end up on the same shard. Now, when I query where related to is 01, I know that I'm not going to have to hit multiple shards to get that data. It's always going to be in one place, right? Yeah. And so this is what you, and then the other thing is that the order ID is it's going to be a GUID of some sort. It's going to be unique and randomly distributed across the key space. So I know that no matter how many orders, or what's that?
Or zoned. Or like regionally zoned. Maybe
you could zone on, you could
yeah.
shard on region, but that's a different use case, right? If you're looking for even distribution, I just want to make sure that I'm using a key that actually is not going to be heavily weighted, right? Now, zone sharding, that might be, okay, look, I've got data in different regions. I want to make sure that the data never leaves this region, or that all data that's in a region is on the same, shard instance. But if you think about regional sharding, that gets tricky because, like, if I do North America versus, Ireland, right? It's, United States versus Ireland, then I'm going to have a lot less traffic in Ireland than I'm going to get in the United States, right? So but there's good reasons why I might want to set a shard up that way, a cluster up that way, but it's not for workload balancing, right? It's for regional distribution of data, right? So a variety of ways to leverage sharding. What I was just describing, using like something like an order ID, would be for even distribution and linear scaling across the cluster. Right.
Yeah. Awesome. So I want to touch on two things related to sharding. What a great question, by the way. And thank you for the comment, Arjun. It's great to know that you're using MongoDB Atlas, our database as a service in the cloud. When it comes to sharding, the first question I get from customers is, okay, so I'm thinking about scale. At what point do I need to think about dividing the database and partitioning it? And the typical rule of thumb is somewhere around 2 terabytes of storage. That can vary depending on the access patterns of your application, but that's the general rule of thumb. When you're talking about terabytes of data, you might want to start thinking about choosing an intelligent shard key to divide your data so that you're not constrained by one.
It's more complicated, right? There's too many dimensions there. You couldn't say at terabytes, right? It's all about how is the data accessed, right? I mean, one of the things about MongoDB is, if we're looking for, fast read performance, then we're going to want to make sure that the working set sits in RAM. Okay, so then it's going to be about how much of that data is actually being read at any given time, right? I mean, if you think about it, if I've got like a year's worth of historical data, but I only access the last 30 days, then I don't care if I got 25 terabytes of data. It's just if the last 30 days fits in RAM, I'm good, right? So
it's conversely. You could have less than terabytes and still have
exactly, and still need to shard, right? Because your write velocity is so high that I can't get up to, that the instances can't handle it. I need more than one shard to be able to process that write velocity, and each shard is only managing a small amount of data, but the data churn is really, really high, right? And that's so this is really, again, it's like so workload dependent, right? It's going to be,
it really is.
When do I shard? I don't know. Let's talk about what you're trying to do, right? I mean, that's what it comes down to. And I know it sounds complicated and there's so many moving parts, and but the reality is there's always these moving parts, and the relational database is not any easier, right? You might be able to say I can get going faster in the relational database, but it just makes a mess, right? If you don't think about the workload up front, if you don't think about the access patterns, and you don't model the data correctly, I mean, how many DBAs in the audience have had to unwind the mess that the developers made, right? I mean, half of us who would call ourselves DBAs have been in there looking at the query analyzer going, what did you do? Oh my gosh, let's partition this table. Oh my God, let's add these keys. Let's add this index. I mean, these are there's so many things that developers do wrong. And we just don't think about it because you can get running fast in the relational database. And what's funny is you can do the same thing in NoSQL too. I can get going really fast and make a big giant mess. It's just a lot harder to clean up the mess in the NoSQL database after the fact, right? But the work that goes into it is not any less, right? If you screw it up, you screw it up, and we're going to have to bite the bullet, right?
Absolutely. So we have another question from Amrit Pal. He's asking about picking a shard key. This is a really important question.
Sure. I mean, we do have some optimizers and some recommendation engines that can do things like tell you, hey, these indexes would be better or not. But I believe with sharding, what it's going to come down to is, you're just going to need to understand how your application's using the data and make some intelligent design choices, right? I mean, I don't want to use a shard key that only has 2 values, right? Like a Boolean value, and then expect to be able to shard across many instances. It's just not going to happen, right? I mean, I've only got 2 values, 0 or 1. So it's going to go to shard A or shard B, right? There's just no other way to route the data. So you've got to just kind of use a little bit of insight into the workload to distill what the best shard key looks like. Right.
It always begins with looking at your data and what your access patterns look like. I mean, it doesn't begin with a common set of rules that have very little to do with your specific application. Like, you're not saying, always separate your data into tables and don't store duplicate information in your database. Like that's not the rule set. The rule set is what does your application store and what are the read patterns look like? What do the write patterns look like? So as a developer, these are things that we should know about our application. And I do want to say that for picking a shard key, that used to be a one and done. Like you were married to the shard key you picked from day one, and that's changed with MongoDB. I think 5.0, we offered redefinable shard keys. So definitely check that out. Okay, so some other questions coming in. Curious about the best way to design our structure. There was one here. Oh, yeah, it's a pity. Here we go. Let's take a look at this one. It's a pity there's no way to use stored procedures and functions. Well, we've got a solution to that. With MongoDB Atlas, you do have the ability to store your logic very close to your data. We offer application services. So what used to be Stitch, then became Realm is now application services, and you can write JavaScript in the cloud, functions as a service that live very close to your data. You get a pre-populated context variable that has an intimate connection to your data, and you can use like stored procedures. But would you answer that in a different way, Rick?
I just think that's one way. There's a variety of ways to execute stored procedure logic, in MongoDB, right? I can run JavaScript, right on the server instance on the head node. I mean, if you want stored procedure, that is a stored procedure, right? It's just JavaScript function execute. We've got Atlas triggers, right, where changes and updates to the data can run very specific stored procedure like functions. Essentially, they're cloud functions that sit on the Atlas backplane, and whenever you make and what I love Atlas triggers because it's guaranteed at least once execution, right? So as long as the operations are idempotent, you can, guarantee that if I make a change to document A, that the stored procedure will fire off the Atlas trigger and execute and write downstream whatever needs to be, or update other documents, or do whatever you need to do. And then the third one was the mechanism you mentioned, but there's a variety of ways to execute complex logic in MongoDB. I would definitely not say that we lack stored procedures. I just think we don't call it stored procedures, but there's ways to execute that complex logic in a variety of ways.
Yeah, awesome. Well, today we're talking about data modeling, some basics. We explained the document model versus relational. We talked about the difference between the terminologies, so going from tables to collections and how those differ. If you've got questions, put them in the comments. We'll try and get to them. We have a few moments left. Let's take a look. Call it out if you see it, Rick, if you get a question. Let's see. Oh, well, this is a good one. He's talking about an API, right? How about events when puts, updates, and deletes? I guess that's over HTTP on the document object. So we do offer an HTTP-based, a RESTful interface to MongoDB. That's available.
Oh, I don't think that's not what he's asking here. What he's asking for is triggers, right? He said, how about events when put, update, delete? Can you trigger an event, right? Or call an HTTP request? Yeah, absolutely. Those Atlas triggers, they can do anything you want, right? They can, you don't have to write documents back to the database. They don't operate inside the context of the database, right? It's a processing backplane. Think of it like Lambda functions in AWS, essentially. They're operating on the side of the database. So whenever a trigger happens, is called down, if you want to call HTTP request and push that change object, and that's the other thing, when a trigger comes in, you get the old doc, you get the new doc, you can do whatever you want with either version. And if that means pass the old document into an archive or do something like that on change, absolutely, you can pass it right down to a downstream system.
Outstanding. And that's all based on go ahead. I was just going to say that's all based on chain streams, which is built into the database. You can use those outside of Atlas as well. Triggers are built into Atlas triggers, but you can also use chain streams.
Oh yeah, chain streams definitely. If you have an on-prem enterprise advanced deployment, you can build your own trigger processor. Essentially, is what it does. Triggers do, as you said, they fire off that chain stream. One of the things, guys, what are the key advantages between MongoDB over DynamoDB? I'm probably uniquely positioned in the world to answer that question. I was the,
I think there's,
the first enterprise SA for DynamoDB, right? Yes. So, and I kind of mentioned it earlier, right? The Atlas platform is really built with a purpose, right? We have integrated functionality from, common commonly requested functionality, things like, full text search, things like, online archive, federated query, right? These are all things that are built into our platform. If you look at DynamoDB, it's just not there. Right, you got to glue all that stuff on there. I can create the same type of functionality, right? But if I want, let's say, for example, an SQL read API and DynamoDB data, okay, they give you Particle, but that's not SQL. If you want to run SQL, you're going to export that data into S3 Parquet files, and I got to write an AWS Glue schema on that, and then I can run Athena queries against that Glue schema. But even just to get it there, I got to do streams into Kinesis Firehose, and now I can Firehose that into those Parquet files. And as a developer, that's like 5 or 6 technologies you got to know. That's multiple APIs I got to call, and then I'm the one who's responsible for maintaining that ETL, right? In MongoDB, I don't have to do any of that. It's all built in. It's behind one API. I query the MongoDB API. If it's the archive data, the query just takes a little longer. You don't have to know 2 different ways to get the data, and we have an SQL API.
Boom. Right. so I want to make sure people understand that. So what you just told me is you can avoid setting up that whole ETL, that whole Firehose, to make sure you don't miss any transactions. And leverage SQL against your database at every layer, at the API
at every layer. And that's the key, right? In DynamoDB, I can export the data into Parquet files and I can run Athena queries, but I can only run the Athena queries on the Parquet files. I can't join the DynamoDB data. But in MongoDB, I can run complex SQL that joins actually the online data with my archive data. And like I said, if your query parameters extend beyond the online data and it goes into archive data, you don't have to know that. We'll do it for you. We go behind the API, we go grab that data, we join it back together, and we send it out to you. So it's one API that developers need. I really appreciate that comment. TW.
I'm voting for you, by the way. I didn't know you were running, but everybody else in the world seems to be.
Hey,
so
I don't know.
I'm
When
voting.
I see things like that, maybe I should, right?
Right. Awesome. I love that. I love good comments like that. Are there any other questions that you want to address before we begin to wrap?
I think that just about covers it. Yep.
Yeah. Awesome. Okay. So we're going to do this every month. Make sure you subscribe to the YouTube channel. It's going to be an indication to us. We're watching who subscribes and how the frequency, or I guess the volume of subscriptions go up as we talk about this. But if you subscribe to YouTube, if you follow on LinkedIn, you're going to get notified when Rick and I are going to go live. And this will be an opportunity for you to ask all those great questions. We're going to take a use case every month and address it and try and explain some of the theory behind it. Rick's real good at that. I'm learning a ton from Rick. So, Rick, thank you so much for joining us today. Anything else you want to say before we wrap?
No, I mean, the questions are still coming in. I wish we could answer them all, but like you said, subscribe to the channel, come on back. We're going to answer them every month. So, we'll have more next month, and really appreciate the conversation. Thanks for having me.
Right on. Thanks, Rick. Enjoy the rest of your day.
All right. Take it easy. Bye.